Review of forces. First of all, let's look at some of the laws that we have for forces. We've got Newton's 3 laws. The first law is the law of inertia. Inertia describes an object's mass, and it says that an object at rest would stay at rest, and an object in motion would stay in motion. So this describes resisting change. I'm going to keep doing what I was already doing. I'm in motion, I stay in motion. I'm at rest, I stay at rest. Newton's second law is best represented by an equation. We typically see it written as F equals m times a, but in reality, it's giving us the best representation of the law by writing it a equals F over m. And all I've done is basic algebra. The inverse of multiplying by m is to divide by m. So now I have F divided by m. The reason I prefer to write it this way is here we can see that values on top show a direct relationship. That means that if something has more force, then it will have more acceleration. Less force, less acceleration. Objects that are on inverses, one's on top and one's on bottom, that shows an inverse relationship. This means that if I want the object to accelerate more, it typically needs to have less mass. And Newton's third law says that for every action, there is an equal and opposite reaction of forces. Where this gets tricky is if we think about let's say a truck hitting a bike. Once that truck and the bike hits the bike, they're going to experience equal forces. And you might say, well, the guy on the bike gets hurt a whole lot more. That hurt comes from what we call acceleration. So because the bike has a lot less mass, it experiences a greater acceleration. Because our truck has a lot more mass, it experiences less acceleration. This inverse relationship is going to cancel so that the forces are equal. So Newton's third law of equal and opposite reactions refers to forces. That unequal relationship between mass and acceleration comes from Newton's second law. Once we know the basics of how to calculate those forces, we can then start to apply multiple forces at the same time. So we have our equation of F equals ma, or A equals F over m. But sometimes we'll experience multiple forces at a time. So if we have more than one force, we refer to having a net force. Just like we saw with displacement. If two forces are in the same direction, then that net force is going to come from adding. If they're in opposite directions, we can subtract. If they're at right angles to each other, we would use Pythagorean theorem. If the net force is equal to 0, we say that that is at equilibrium, meaning that all of the forces are balanced. If I'm pushing in one direction at 5, then I'm being pushed in the other direction at 5. Now, being at equilibrium means that we do not accelerate. Now, this doesn't mean we're not moving, it just means we're not accelerating. So we could stay at rest if we were at rest, or we could stay in motion, just at a constant speed. Other particular forces that you should remember. Normal forces, and that's where something is sitting on a surface. The surface is pushing up, like a table. Frictional forces, and that's going to be that opposing force. If I'm trying to slide down the hill, then friction would try to keep me up that hill. applied forces. And that's just going to be a push or a pull. Tension, like a rope. And probably the most common one, weight. Weight is a force. Mass describes what you're made of. Weight describes the force of gravity that affects that mass. So weight is going to be the mass times the acceleration of gravity. On Earth, that acceleration is negative 9.8 meters per second squared. When we refer to that acceleration of gravity affecting something at negative 9.8 meters per second squared, we call that free fall. Free fall is falling in the absence of all other forces but gravity. No air resistance, no parachutes, no strings, no bungee line. When things are falling, they're accelerating. Because they're accelerating, we will use only equations that have acceleration in them. So one of our initial equations of the change in velocity over time, and commonly we will have to find the final velocity. So it's good to recognize it in this form as well. We're not always going to be given the time. So another equation we have from our formula chart is the final velocity squared, initial velocity squared, divided by 2 times the distance. Again, a lot of times we have to find the final velocity. So a little bit of algebra. I'm going to cross multiply. A equals 2 times b. Bring down my other terms. Inverse. Inverse of subtracting initial velocity is to add it to both sides. Don't forget to carry your square. Bring down my last term. And the last step that I could do would be to take the square root of both sides to cancel out that squared. The final equation we have that has acceleration from our formula chart is to solve for the displacement of something. So we look at the initial velocity times time plus 1/2 at squared. Very commonly, the initial velocity on all of these is oftentimes 0, especially and always if we're talking about something being at the top. If we start at the top and fall down, the initial velocity is 0. The acceleration is still negative 9.8, but at the top, the initial velocity is 0. So we can simplify this one to 1/2 at n squared, because 0 times anything is 0. The other common way to rearrange this one would be the time that it takes something to fall would come from, and I won't show the algebra on this one. I'm showing the y here because remember that we're falling, and we're using gravity to do that. So these are kind of my common equations, and you should recognize them in the different forms. If things are falling, but not only due to gravity, then they're not necessarily in free fall. When we have multiple directions of motion, we have what we call a projectile. We're having 2 dimensions of motion. So here I could be rising while moving forward, rising while moving forward. And I'm going to slow down while still moving forward. Eventually I get to the top where I'm no longer rising, so my vertical velocity is 0, but I still have horizontal velocity. And then as I start to fall, I'm going to speed up in my vertical direction, but still maintain that forward velocity. This is what we call a projectile. Projectiles follow the path of a parabola. So rules that we have are vertical velocity. We are accelerating because of gravity. So we will use those 3 equations we started with, our 3 acceleration equations. Horizontally, we don't have any gravity, So we have constant motion. The only equation that we have that shows constant motion is our very initial one. So we'll represent it with some x's here. No acceleration because it's constant. A few other nice rules to remember about parabolas. On a parabola, if this was graph paper, then the value that I have here would be the same as the value that I have here. But one would be positive, one would be negative. So I could move up at a speed of 10 meters per second. And over here, same spot, I'd be moving down at negative 10 meters per second. I could still be moving forward at the same time. And that could be any value, 2 meters per second. But because it's constant, it would still be 2 meters per second over here. To figure out if something is moving down and forward at the same time, their relative velocity, or what you actually feel, we're again looking at kind of that Pythagorean theorem method. So I'm moving forward and down, I've got my triangle shape. So I take my x velocity and my y velocity and plug it into my Pythagorean theorem to find the result, or the relative velocity. So my resultant velocity would be my a squared and my b squared to solve for my c squared.